We've seen one kind of multiplication involving vectors, and that is scalar multiplication. And that's when we take a number c in the real number system and multiply it by a vector we'll call a. And if a has components a1, a2, and a3, then we see that the components from scalar multiplication are ca1, ca2, ca3. There are two types of vector multiplication. They're called the dot product and the cross product. In this series of videos, we'll look at the dot product, and the cross product is reserved for a different series of videos. The math definition of the dot product says that if we have two vectors, a and b, with components a1, a2, a3, and b1, b2, b3, the dot product is a dot b, so there's a dot between them. And I'm going to pause right now to say, if I'm multiplying 3 times 5, we can use that with we can write that with a dot. Or 3 parentheses 5, we have the same thing. And if we're looking at 3 times x, we eliminate the dot entirely. That's not an option with the vector multiplication called the dot product. The dot here is actually required. It's computed, well, it's written down as a1, a2, a3 dot b1, b2, b3, and this can be written using angle brackets or IJK notation. It doesn't matter. If it's IJK notation, then parentheses would be in order. But this is computed by performing a component by component multiplication and then adding the results. So a1, b1 plus a2, b2 plus a3, b3. As a quick example here, if we let a equal the vector 2, negative 4, 7, and b be the vector negative 1/2, 5, 13, then a dot b is going to be 2 times negative 1/2, and so negative 1, plus negative 4 times 5, so that's actually going to be minus 20, plus 7 times 13, and so 91. So the result is that a dot b is 70. And we would get the same result, again, if we used IJK notation. There's a relationship between what we've just done in matrix multiplication. If we consider a row matrix that has entries a1, a2, and a3, and a column matrix that has b1, b2, and b3, then matrix multiplication would say multiply a1 by b1, a2 by b2, and a3 by b3, and add the results together. And the result would be a 1-by-1 matrix that has a single entry. We aren't going to be doing anything with matrices in this course, but if you're familiar with matrix multiplication, then there is that parallel. The parallel is there whether you're familiar with matrix multiplication or not, but if you are familiar, then you can see the parallel. Let's make a note at this point. You can see it on the screen here. The result of the dot product is a scalar, a real number. Now, we are going to see this in different contexts throughout this course, so I'm going to say, or a real valued variable expression in the event that the components of a and or b have variables in them. We're going to see that before we're done with this course. But really the point is not whether it's just a real number or a variable expression. The point is that it's not a vector. Okay, so we've multiplied two vectors together using the dot product. The result is a scalar and not a vector. Very important to keep that in mind. We do have properties of the dot product. Not going to go over all of them, but we can see that, for instance, a dot b is b dot a, so it is commutative. Associative property holds. The first one is interesting. The magnitude of a dot a is equal to the magnitude of a squared. We're just going to look at that first one here. So if a is equal to a1, a2, a3, then when I dot that with itself, I end up with a1 squared plus a2 squared plus a3 squared. Note that the magnitude of a is equal to the square root of a1 squared plus a2 squared plus a3 squared. Well, that's a wonky looking radical. Anyway, and so we can see here that the expression that we ended up from the dot product is the magnitude squared. I encourage you to go through and confirm those properties for yourself when you have a moment. We've seen the math definition, now we're going to see the physics definition. Physicists define the dot product to be A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, so cosine of theta. To see this in action, we're going to revisit our example. We had A was 2, -4, 7, and B was -1/2, 5, 13. The magnitude of A, as you can confirm, is the square root of 69. The magnitude of B is equal to the square root of 194.25, nice round number there. The magnitude, A dot B is equal to 70 from our previous work. So using this formula that we just wrote down, this physics definition, we can say that the cosine of theta is equal to 70, the dot product, divided by the product of the magnitudes of A and B. So 70 divided by 69 times the square root of 194.25. Using then an inverse cosine, we can find out that theta is approximately 52.8 degrees. That angle is the angle between the two vectors A and B. Now we're going to see a justification for the physics definition. We have here a diagram with two vectors A and B, and I am drawing the vector A minus B. You can confirm that using geometry that is the case. And let's recall the law of cosines. It says that c squared is equal to a squared plus b squared minus 2ab times the cosine of c. Important thing to keep in mind here, that the c squared on the left-hand side of this equation and the angle c on the right-hand side of the equation are opposite each other in the triangle that the law of cosines is being applied to. Applying that to our figure, we see that the magnitude of a minus b squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2ab, magnitude of a, magnitude of b, times the cosine of theta. Using some properties of the dot product that we just saw, the left side can be written as a minus b dotted with itself, a minus b, and the right side is then equal to a dot a plus b dot b minus 2 magnitude of a, magnitude of b, cosine theta. That didn't change at all. The left-hand side essentially becomes a FOIL situation where we have a dot a minus a dot b minus b dot a plus b dot b, and the right-hand side remains unchanged. Subtracting out matching terms, and remembering that the dot product is commutative, we end up with -2 a dot b is equal to -2 magnitude of a, magnitude of b, cosine of theta, and dividing by -2 yields the definition that we alluded to before. As a consequence, if theta is equal to pi over 2 or 3 pi over 2, then a dot b is equal to 0 because the cosine of pi over 2 or 3 pi over 2 is equal to 0. In other words, the vectors meet at a right angle. Two vectors that meet at a right angle are said to be orthogonal. That last bit is just a little bit of vocabulary.